today to introduce to you one of our distinguished speakers, Caleb. Caleb has very, very interesting stories. He already showed us one 4 years ago during the pandemic, and it was also very well attended. I think it's like 40 people there. And we saw the truck actually drive by itself on the highway from Arizona to California. How cool is that? So Caleb has distinguished speakers. I feel like everybody with me that day all agree. And I cannot wait for you to enjoy his talk today. So Caleb, it's all yours. And when we never mind us, we will figure out our technical problem like in 5 minutes. All right, so feel free to start.
All right, awesome. Well, thank you so much. That was it. I think that's actually like a lot to live up to. We'll see whether this talk actually rivals the one that I gave 4 years ago. I have to say that the open source software that I've been doing in the interim does not involve massive vehicles barreling down the highway, but it is actually at least in some ways related to the work that I was doing then. So I think I'll just start off by saying, can everybody see my slides here? I think I'm sharing right now.
Yeah, we can.
I haven't used WebEx before, so I'm not sure. Great, okay, so just as introductions. So we'll get into it. So who am I? So I attended UW Whitewater in 2012 as a high school student. I believe the department was just starting then. And that's when I met Professor Wen. And so I did a little bit of research for the department at that time, but obviously it was just like fledgling stuff. I think it was stuff like generating 3D trees and stuff of that nature. But I think that definitely like cemented my interest in computer science. And so when I went to UW-Madison, I majored in computer science and graduated in 2017. I went on to work on autonomous vehicles for 5 years in Silicon Valley. And that actually is the presentation that I gave that Professor Wen is referencing. And so at the time, I think I gave a presentation just about the kind of stuff that I did on the data visualization team that I led. And so I think most engineers, when they hear data visualization, they think immediately of plots, as in I was just, basically making plots all day. And it is true, we had lots of plots, but it was actually a high performance blend of 3D graphics, sensor data, and some other stuff. And so it was really akin to a game engine. And I think the thrust here is just that it allowed engineers to quickly understand what was happening to one of our vehicles, both on the road live and unrecorded data, and understand why it made the decisions that it did. And so that was a very cool application of the skills that I learned in school. And so the company, which was called Embark Trucks, went public in 2021. And so suffice it to say that I've had some freedom to do other things since then. And so I'll start this off with something very scary, which is always like, a demo is terrifying, but I've been dog feeding the software for a long time. And so I hope it goes well. So let me just share that window here. Let's see. Nice. Okay. So just everybody can see this, right? So, yeah. Hello. It's all good. Nice. Okay, cool. Thank you so much from the audience. So anyway, I'll start up Sai. So this is Sai's splash screen. So I haven't introduced anything about Sai yet, so I'm aware of that. So Sai is a terminal multiplexer in the vein of screen, TMUX, etc. If you have never done any significant work in the terminal, this term probably will not mean anything to you whatsoever. And so I'll explain all of that in a bit, but I just wanted to start off with a demo first. And so I should clarify that this probably will not make very much sense right now. For example, I'm not actually showing the keys that I press to make things happen on the screen. See why that matters in a moment. But it's just to give you a general feeling of what Sai does, why it matters, and that sort of thing. And I'll get into what specifically it is a bit later. But this is it. So press any key to continue. So Sai is a terminal multiplexer, and so it's opened up a terminal session here, just like you would find in TMUX or Screen or something of that nature. And so it's just a standard shell. And so I can do anything that you do in a standard shell, something like running htop, get out of that, print a bunch of numbers, echo hello world. So why does psi matter? Well, psi matters because you can go back in time. So I can replay everything that I just did. I can pause, I can go back and forth, and see exactly what the contents of my screen were, say at, this particular timestamp, and even play it back, backwards, forwards, etc. Right? And so that is its core functionality. I can also do things like searching the contents of the screen for something that I know occurred. And so this is showing me like all the instances of when this particular string that I just typed was on the screen. And so you could do things like the standard stuff that you find in other terminal multiplexers, like copying text. And so important thing to note here is that you can copy text from any point in the history of the terminal screen. So I can go back to real time and see that the text that I copied is pastable and nice. And so yeah, anyway, so that's the core functionality. I think everybody gets excited about it. At least I do. I mean, come on. So anyway, so you might if you've ever worked in Bash, you might be familiar with like Control R, which typically is functionality. I can just use the built-in. This is actually not this is FCF's Control R here, and you can quickly search for a command that you've already run, and it uses Bash history. And I found that it just wasn't very good. And so psi comes with a built-in Control R. And so this is it stores all the commands that you run in a SQLite database and allows you to go back in time and revisit them. And so you're wondering like, well, this is functionality that is present in a lot of different solutions to this. But the key with psi is that in addition to seeing the commands that you've run, you can also see their output. And so, in other words, like you can explore all the commands you've ever run, see their output, etc. In addition to that, I can not only like use that just for like standard Control R. So say I wanted to like run this command again, bam, we have Control R here. I can also go back and explore other output that occurred around that command. So this is a session from the 21st of September, right? And now I can back and look through all of the output that occurred at that time. So in effect, I'm throwing a lot at you, and I understand that. But the point is that it records everything you do in the terminal, all the work that you, all the sessions that you run, and allows you to search through them and revisit all the commands that you've ever run. So crazy, right? This is actually very similar to, as I saw this in the comments of Microsoft Copilot recall. I think that there's been a lot of fuss, like hype around similar technologies that work across your entire computer, so that record your entire screen at once, and use some OCR among other things to let you like search through that. But the thing about those kind of solutions is that they're really just like taking screenshots at some cadence and allowing you to search through them, and so it's not actually video. Whereas in the terminal, you can do all that quite easily. And so I think like the really killer stuff is this is an example that I actually used once, but I'll search now for like across all of the sessions that I've ever recorded for a string. In this case, OpenAI. And so what it's doing is it's searching, like right now it's searching through thousands of hours of recorded sessions. And it just found the first time that I ever typed OpenAI in all caps into my terminal sessions. I guess this is, I guess you can see here, it was on the 21st of January, where I'm actually typing in an API key. So I've already invalidated this API key, so please don't go try and use it to run up my OpenAI API fills or something. But anyway, so just an example of the power. So like, for example, like, you're able to find exactly when something happened, when you did it, in my case, like whatever, 10 months ago. So pretty crazy. And anyway, so yeah, so I'll just like show you one more thing that's pretty neat. You can, it works sort of like how Jupyter Notebooks do, where psi has like some special functionality where it can analyze a terminal session to determine like the output of every command that you run. And so this is something that has never existed before, but I can recall the output of a command and type it back into some other program. So in other words, like without rerunning a command I've already run, I can just get its output. And oh no, I cannot. Oh, maybe. I think maybe I messed something up, but oh well. That's embarrassing. Oh, I know it worked. It did work. I just I'd run some other commands. Anyway, so this is running it. It's grabbing the output of a previous command and allowing me to pipe it through grep, as we can see here. So this is a kind of a ramshackle demo. I'll switch back to the slides here, uh, and we'll move on. So yeah, so what will this presentation cover? So what is a terminal multiplexer? I'll cover size, origin, and philosophy. And I think of probably the most academic interest, the search algorithm, which allows me to do that, like what I did in the demonstration of finding a string that occurred in a terminal session on the screen, in this case 10 months ago, in a performant way. That's something I had to write myself. And so for those of you who actually do real research and aren't just messing around writing code, that'll be interesting maybe, among some other things. So anyways, what is a terminal multiplexer? Another way of thinking about this is who cares? A terminal multiplexer is a task switcher for the terminal. It's sort of similar to like the windowing systems that you find in your operating system. So they have those abstractions of windows and desktops and being able to move windows around and such. It's basically the same thing, but just inside of a terminal. And so it's a way of accessing many terminal sessions from just one session. In the past, this was much more necessary than I think it is today, despite the fact that people still use these all the time for doing work. The reason being is that, if all you had was a single terminal, a physical terminal, like a VT100 that you'd connect up to a computer, and that was like your only way of interacting with the computer. You definitely wanted a way of being able to switch to multiple terminals and like retain the status of your work over time. So anyway, so I think I'll probably take a moment here just to evangelize like why do software development only in the terminal. I think that Unix tools and command line tools are still extremely powerful, and I think it behooves you as a software engineer to learn them, at least learn them, if not use them all the time. Some cool things that I like about doing all my work in the terminal is like, you configure it once and run everywhere on any Unix-like OS. It makes doing development work on remote systems very nice. Same in the cloud, and your sessions persist. I think the coolest thing about working in the terminal is just being able to expose like a single TCP port, like your SSH server, and then having access to your entire development setup remotely. And so anyway, so why'd I start writing Psi? Forgetting things sucks. So as I mentioned, I worked on robots in 2019. Well, it was when I was working on robots in 2019. I had these problems all the time where like I would fix a problem and then on one of our vehicles, for example, and then it would occur like 3 weeks later, and I like had no idea how I fixed it last time. But I had accessed our vehicle over SSH, and there are actually like several instances where, because I couldn't remember how I fixed a problem, I caused complete failure of one of our vehicles. And so this is something like, the truck in our case would, lose its power steering and it could no longer accelerate, and they had to pull over on the side of a desert road for, half an hour to an hour while we figured things out. This is, I think, beyond the lesson of like, you should maybe you should record your terminal sessions. I think the lesson maybe is just don't give 22-year-olds lots of venture capital. But anyway, so yeah, I wanted to be able to like, I just thought it was dumb. It was like, why, like, terminals don't produce very much output. Like, why can't we just record everything? And I should just be able to search through it quickly and easily. And so anyway, so terminals are just text, right? And so it's light. It doesn't occupy very much space on disk, and there's no excuse, right? Bash history is bad, and actually, in addition to this, like tmux history is bad. But anyway, I think the thrust is just that, like, from my perspective, you should be able to remember or be able to recall every command that you've ever run, right? And that should just be a function of your terminal. And I don't understand why it hasn't been in the past, because I want to know that stuff. And I think that like Bash history, for example, has a habit of like periodically throwing out or just missing some of the commands that I run. And I'm sure there's just something that's been misconfigured for my entire software development career, but whatever. So anyway, in addition to that, terminal multiplexers had stagnated. TMUX and Screen have had no real like new true feature work for a long time. And new upstarts, such as, I think it's pronounced Zellage, I'm not sure, did not go far enough. In addition to that, like, yeah, Rust is not a feature. I think that there's a lot of sort of alternatives to the traditional tools that people are writing these days, and mostly they're just clones, but written in Rust. And this has been a phenomenon for like, I mean, I swear almost 10 years now, but it still hasn't changed the fact that I think when you make something new, you really have to do core new feature work. And so I wanted a fresh start. And I think that the broader goal of this is to attract folks back to using the terminal again. And so what does a terminal multiplexer look like in 2024 if you started from scratch and tried not to follow like the UI legacy of everything that came before it? And so there's been some motion in this in like the terminal emulator space, which this is distinct from a terminal multiplexer. It's like iTerm, Xterm, Kitty, Warp, and Alacrity are ones that I mentioned here. And these are like the actual applications that I guess that you usually use to interact with the terminal. But yeah, it's like there's been like some interesting functionality that they've introduced, but I just don't think it's gone far enough. And so that's kind of why I started Sci. I also think the terminal is amazing. Like even without changing standards, like you can do so much, and they could be much more than they are in part by just having access to all the stuff that you do. I think that like there's lots of constraints in like actual GUI applications that are not present in the terminal, and so that's a really powerful thing. And so yeah, like I mentioned in the other slide, like making the advantages of the terminal even more obvious. Building a development platform where everything you do is recorded and easily searchable. And like I said, revisit the paradigms, make something beautiful. So yeah, the main topic of this presentation is the search algorithm. And so I'll start off with just a problem statement of like why this matters. So given the recording of a terminal session and a query string, return all of the instances where sequential screen cells like match the query. And so I think that like if you've used a terminal at all in your engineering career, you're familiar with the fact that if you like scroll up, like I'll do this right now, actually, if you scroll up, you can see like the previous output of the terminal, right? And usually your terminal emulator will allow you to search that, which is what is referred to as like the scrollback, right? The scrollback buffer. But that's actually not what this is, right? So what we're trying to do is we're trying to like come up with an algorithm that allows us to search over the history of the screen, right? So even if you open things like a full screen application like Vim or HTOP, like I did earlier, you still want to be able to search through what was actually visible on the screen, right? And that's like a somewhat tougher problem. And so, yeah, that is like one of the basic features that I wanted to implement when I started Sci. And so, and some important considerations for this is like you want to get the entire time range that a match was on the screen. And so, in other words, like for this entire stretch of time, a match was present, right? And that means that like if the terminal screen is cleared or you like close Vim or something, you want to make a note of that and either stop the match or keep it going. And so translations also don't invalidate a match. So like for example, when your terminal gets to the bottom of the screen, all of the lines move up by one, right? And that shouldn't invalidate any matches that are currently on the screen. They should just be shifted. And so queries can be regular expressions or literals. In practice, like I just turn all literals into regular expressions by commenting out any special characters. But anyway, so I have to start from the top though. So like, what is a terminal emulator actually? It's a computer program that emulates a video terminal. So back in the day, I have no personal experience with this, but back in the day, you needed an actual device called the video terminal that plugged into your computer, and that had a keyboard and that you used to interact with the computer. And so nowadays, we just emulate these and call them terminal emulators. The standard for this is actually just vibes, is how I describe it. And I know this because I mentioned this, but I had to write this mostly on my own. there's some like informal standards that have been passed down, but largely based on the original VT100 quote unquote standard. But there have been so many extensions over the years that it's really just a matter of like digging up obscure information on the internet. So that's a lot of fun. And so how, like, what is a terminal screen actually? It's the visual state of a terminal emulator. It has a two-dimensional grid of cells. It consists of a two-dimensional grid of cells with a cursor. And so, as you might already be familiar, each cell has a Unicode character. Like I mentioned here, some characters can be wider than one cell. This particular point cost me definitely weeks and weeks of my spare time, just in realizing that I didn't handle characters that were wider than one cell. These, each CJK glyph is actually 2 cells wide, so that was fun. Like a color, styles, etc., and that's really it. And so everything else that you're familiar with in a terminal emulator is really just a feature of that terminal emulator. It's not actually inherent to inherent to what a terminal screen actually has to support, right? And like this distinction might seem kind of academic, but it's really just like when you're implementing a terminal emulator, you're really just implementing a state machine that correctly affects the state of the screen, and that's it. So yeah, I mentioned this. Yeah, so terminal emulators are just state machines that accept byte strings as input, and most of the time, these just like printable characters, for example, are written directly to the screen and move the cursor in ways that I'll get to. But certain byte sequences that do not produce immediate visual changes. Among those things like moving the cursor, handling new lines, changing the color of the current, like the next cell, that sort of things. But the set of things that can happen in response to a byte sequence are fixed, right? So you can set the cell under the cursor and move the cursor forward. I'm skipping over a lot of details, but basically, yeah. So clear region of cells or scroll a portion of the screen, and that's really it. And so I just have like some basic demonstrations of this. So like if I write foobar, this byte string, it's just written to the screen, right? But if I write foo and then move the cursor to a particular line and column, then it just writes. So for example, here we have this this byte string here, which consists of foo, a special sequence, and then bar, right? And so this special sequence moves the cursor to line 2, column 2. So in other words, like foo is written, move to column 2, line 2, and start writing bar. And so this is actually like a pretty serious problem when it comes to writing this algorithm, because like you have to handle matches that that could occur when the cursor is moved into place and then writes a cell that completes an existing partial match. And so it's pretty tough. But anyway, so what is a terminal session? So it's all of the data that's written to a terminal emulator with timestamps. So this is actually was a surprise to me when I started writing Psi. Like terminal emulators, they just interpret a stream of bytes and write your key presses to the controlling program standard output. This is rephrased as like you can reproduce the visual state of a terminal only using the bytes that were written to it since the beginning of time, so to speak, and any resizes that occurred, right? And so in other words, like if you record all of the bytes that have ever been written to a terminal along with timestamps and the resizes, like when the terminal window was resized, for example, you can actually reproduce the state of a terminal. And so that's how Psi works. So yeah, so an aside on this is that Psi records all of the terminal sessions that you run. In other words, just like the panes, right, in TMUX's parlance, to Borg files. Get it? Yeah, right. Very funny. Cyborg. I don't know. I don't know why that was a decision I made. But anyway, so this has actually been around for a long time in various forms, but I've never seen it all composed together like this. So the script tool from 1979 was the first to do something like it. But yeah, it really just, it recorded the output of some program and allowed you to replay it in your terminal. And so there was no like playback functionality like I demonstrated earlier.
Yeah.
And so I'm going to walk you through very basically just 2 attempts that I made at solving this problem. And so I got to warn you that I've been going through this material kind of quickly because getting to this is actually, it takes a lot of background, but it's also quite complicated. But this is the first attempt that I made at solving this problem. And so I'll actually just show all of it at once so you can really absorb it. And so we have the state of a terminal screen below right here. And so what you do is you convert each cell to the byte representation of its Unicode character. So these are all just at like standard ASCII, you know, alphanumeric, and so it's fairly simple to convert these to bytes. But in other words, like this, you turn the whole screen into one long byte string, right? And so in other words, like, you know, once you get to this character, it continues on to the next. And so whenever a cell is set, for example, like when a printable character is actually written to the terminal, you run the regex engine that has already been like with the query string that we already compiled to a regex. You run it on the cell and you see how many, like you see whether that cell was consumed by the regex engine. I'll admit this is a little bit abstruse, but I'll explain this for a little bit. But anyway, so for example, like in this case, we have the query string of BA and then this character class of A to Z, right? And so in other words, like bar, baz should both be matched by this. But in this case, we've seen that like this terminal has B and A written to it. And so when the B is originally written, what we do is we run the regex machine just starting on this B, and we say, if this cell is consumed, as in like if it's a partial match, the regex engine tells us that it's a partial match. And I'm skipping a lot of steps here because this is actually like fairly complicated to set up, because partial regex matches is not really like a common thing people do. But anyway, so in other words, like if this cell was consumed, we know for a fact that it must be a partial match. And so we can start tracking it. And so in other words, like once NA rolls around, we can also pass that into the regex engine and say definitively that it adds to that partial match. So now we have a B and an A, right? And so we're tracking this partial match that begins at this cell here, and waiting to see whether like any subsequent bytes will complete that partial match and turn it into a full one. And so simultaneous to that, like all of the complete matches, as in the ones that actually match this regex pattern, we hold a reference to and ensure that anything that happens to the terminal, the state of the terminal screen, does not break any of these existing matches, right? So that's things like moving the cursor to one of these matches and overwriting a cell, for example, with a cell that is not matched by this pattern, or even just clearing out one of these cells, right? And so we're not only tracking to see whether new contents of the screen match the pattern, but also ensuring that no existing matches are broken, so to speak. And so this is it's pretty hard to wrap your head around, but just this works on the basis of the fact that like you can just pass bytes one by one into sort of an imaginary terminal emulator that you're just simulating in memory, and determine like what the state of the screen was at every time step, so to speak. And so that's how you actually able to search the screen. And so it turns out this is like horrifically slow, and this might be obvious to those of you who like actually do research in computer science, and aren't just armchair enthusiasts. But the real problem is things like, you're going to have a lot of partial matches. For something like this pattern here, we have A with a character class of ABC, right? So like every time that A occurs in your screen, you're going to be tracking that and waiting to see whether it's ever like this character class is ever satisfied, right? And so, yeah, you can't know ahead of time whether like a match will just be partial forever, right? As in like, yeah, it'll never actually turn into a full match that is matching the whole pattern. So that's pretty game stopping, I would say. But yeah, so anyway, like the way of getting around this is what I would call just like cheating, right? So because we record all of the bytes that have ever been written to a session, we can just, compile the regex and check to see if there are any matches in the entire sort of like the byte history of the session, right? And that what that spits out on the other side is just like this like particular byte offset, right? You can check to see whether there is a complete match that exists on the screen just behind the cursor, right? And I think you might have some questions about this, like why not just do this in the first place? And the basic reason is that it misses a lot. Like there's a lot of programs that don't actually write sequential screen cells sequentially. And by sequential here, I mean like, in order, like this way, like, from left to right, top to bottom. And the reason being for that is that like they might change the styling of the next cell, which, it consists of like a terminal escape sequence, they're called, right? It's just a special byte sequence. And so in other words, like your regex will no longer match, even though the contents of the screen will actually have a match, right? And so, yeah, it's a problem. It's basically by saying like by throwing out a lot of potential matches, you can save just incomprehensible amounts of compute, right? Because before this was a very slow. It takes several minutes just to run on an hour-long recording, right? But yeah, anyway, now it's much faster, right? Because yeah, like I said, you get the byte offsets of all of the like suspected matches, and you can just jump to those and check to see whether the contents of the screen contain a full match and track them if necessary. Yeah, so what's the end result? So I can search through thousands of hours of work, recorded work, right, that I've done in the terminal in just a few seconds. Performance is really just bounded by the number of full matches, as in that actually appear on the screen. And so usually, if you can get specific enough, like I showed earlier, that OpenAI key, right, it's actually fairly fast. So anyway, so I'll talk now just a little bit of the side development process, like also titled Fun with Golang. Yeah, interestingly, Go has become the default choice for writing terminal applications, and Psi is among them. So it's entirely written in Go, even though it uses a scripting language, which I'll get into a little bit later on the slide. It uses a scripting language called Janet, which is a Lisp for its configuration language. And the reason for I think Go's ubiquity in this field is just a project called Charm Bracelet, which in recent years has just published these amazing libraries for making interfaces in the CLI. And the funny thing about this is that like I actually didn't even end up using these libraries as like the main libraries people use for like making UIs. I had to write my own just because of like some insufficiencies. But anyway, what else is great about Go? Concurrency is fun and easy until it isn't. I mean, it's really cool being able to just like, spawn up a bunch of Go routines and do a bunch of tasks in, whatever the green threads coroutines. But yeah, you still run into the same like very annoying like data races, etc. And so I found that like I still occasionally spend many hours debugging strange issues and like hard to reproduce timing issues. And I think that's probably just like the nature of the beast. The downside of using Go is that I had to write my own terminal emulator and bindings for the scripting language, right? Which involved a lot of reflection. And so if you're not familiar with reflection, it's really just like being able to observe and change program behavior at runtime. Mostly this is used for like a good example. The best example of this is like JSON serialization and deserialization, where you're like taking like some bits of data that may or may not correspond to a data type that you already have in your program and try to like match it. And you have to do this when you write bindings for like a scripting language where like, well, in a scripting language traditionally, it's just like, dynamically typed. It's where everything goes really. And you have to like fit that back into Goland, so to speak. And yeah, and like that's the thing about reflection. It's like, I really like Golang, but it's really fun vanilla JavaScript where you can do whatever you want. And sometimes you just panic from from something you didn't expect. Or about like your Go program just panics because of some form you didn't expect. And that's like frustratingly common. And so it's a way of stepping outside of, I think, static typing, and that's kind of scary in a way. So one cool thing that I wasn't even sure if like I would have time to demonstrate, but hopefully I can show here. Yeah, so all of like size usage examples are generated in CI, and so it's like things like this where you can see I have these like basically like this player that lets you play back usage of Psi. All of this stuff is generated in CI, and so every time that like I push a commit, all of like the usage examples of Psi and its complete documentation is just regenerated, and that's pretty cool because it works sort of akin to like Storybook if you've ever used that in like the web development world. But it's definitely like allowed me to make what I hope is a very easy to learn application. Yeah, so let me just hop back to my slides here. And yeah, where is this window? Nice. Nice, all right. Conclusion, yeah, so programs should be weird. When is the last time a program made you feel something? I think this is kind of like a crazy thing to say about just like some random open source software, but like I have this feeling that it's just like most of the programs you use are just cold and utilitarian, and like I really like didn't want that for Psi. And so I'll actually like show you something in a moment that proves this. But Psi is weird, and it could be weirder. Write more weird programs. When I was living in Brooklyn at one point, I stumbled across a conference that was in part hosted by the School for Poetic Computation, which is just it's a school that teaches a blend of engineering and art that I thought was really cool. And so yeah, anyway, so Q&A. So we reached a Q&A, hopefully right on time. So these are just like some potential topics should you work for a startup, New York or San Francisco. So why is Psi weird? This is actually something that I didn't even show in the demo, but I intended to. You know, that's how demos go. I think I was just flustered from it not working correctly. Now you should see this. So Psi has actually open up. Let's see. Name.go. So in addition to having a command palette, which is pretty fun, right? Psi also has a bunch of animations, including, and this is surprising to people, a working fluid simulator. So, yeah, so basically like whenever, so Psi has a built-in like fuzzy finder, which I didn't actually show in the demo. There's a built-in fuzzy finder, and like whenever you fuzzy find something, it takes the contents of your screen and passes it into an animation, which is pretty neat, I think. But yeah, so it is a real fluid simulator, which I thought was funny, very weird. But hey, I guess if it's your project, you can do whatever. So I'll get back to, actually, while we're doing Q&A, I thought this would be kind of funny. Where is this window? I found it. Nice. Okay. So this is actually the Psi session where I wrote this presentation. So while it's playing back, when I was working on this last month, you can ask me some questions.
Great. So it's now open to the questions. So Caleb has many good experience to share. So first of all, we'll focus on the question on the side, the presentation itself, and then second of all, I have some questions that I'm dying to ask him already. So we'll open the question. If you have questions, please unmute your microphone or type it in the chat. So and there's one question in the chat already that was asked maybe at the very beginning of the talk by Mike Jorin, who's also a fellow graduate from UW-Madison. He said, is it like how Microsoft Copilot recall? That's one of the questions.
Yeah, I sort of, as an aside, answered the question kind of, but I think I'll expand on that point a little bit more. It actually was, so to be clear, I actually started working on this, I think, before even that was like announced as like an upcoming feature. But I would say like this idea has been kicked around for a long time, like recording your screen and like finding some way of returning to it. And I think that my perspective on this is like, because of the inherent diversity in like the kinds of things you'll do when you're using traditional GUI applications, like playing videos, like all applications do things in a different way. Like it's a very hard to like generalize that kind of functionality to make something useful. Whereas like in the terminal, like because it's just text, right? I think that it's a lot easier to capitalize on the fact that you're recording everything. And so, yeah, that's basically the thesis. And also on top of that, I actually mentioned this in like the synopsis for this presentation, but like all of my, oh yeah, it's so funny that you just mentioned this question. But yeah, so I've been using Psy and recording all of my terminal sessions for maybe over a year now, maybe like 15 months or something. And that amounts to like thousands of hours of work, both when I was working full time and then also just doing my side projects. And if you had to guess how much it takes on disk, like you'd never guess how little it is. It's actually only about 200 megabytes. So that's like it's like unbelievable, right? And this is like full fidelity recordings, thousands of hours, and it occupies 200 megabytes on disk. So that's pretty crazy.
That's crazy, yes. That probably answered Cooper's questions. Cooper put in the chat, how much space does storing all the history take up? Is there any limit on how far you can go back?
So there's no limit. I really like skimmed, the problem is like this, my time was so constrained in this presentation that I kind of had to fly through it. It was hard to find a good balance here. But yeah, so everything is recorded. Everything you do is recorded, and you can jump back to every command you've ever run and see the output of like what the visual, like the screen was looking like at that time. So in addition to that, like all of the commands that you run, by that I mean like strictly like the command, like echo whatever, all of that is stored in a SQLite database, and so it's very quickly accessible from the scripting language that Psy uses. And so, in other words, yeah, you can very quickly like when I showed Control R in the beginning, that was searching through all the commands that I've ever run in Psy, which I've only actually had that feature around for a few months, and so there's only like maybe 1,000 commands that I've run. But yeah, it's still pretty cool. Being like, I don't know, early September, like I ran this command and like this is what happened, and like being able to jump back and just like copy text from that is really cool. It saves your life when like, for whatever reason you didn't save something or whatever. It doesn't matter. You can just go back and copy all the text that was in that file and you're back in business.
Great. So I have okay, so Mike, I have another follow-up question. What impact does Pi have on terminal performance? Does it introduce noticeable latency?
So it's a great question. It's actually something that I've been thinking about lately, but I specifically structured Psy so that like like the specific aspect of recording sessions does not contribute to any latency issues. Where the latent, as in like all of the writing to disk and all that just happens in another thread, right? And so it shouldn't block actually running near the screen. Where latency does come into effect though is like terminal multiplexers are inherently like compositing the output of the screen to produce the final result. And so this is a little bit abstruse again, but it's like that introduces latency. And yeah, so I think right now it's something on the amount of like, at least on my MacBook M2, something like 30 to 50 milliseconds. I'd like that to be less. I think that's like kind of crazy high. I should point out that that's actually still much faster than tmux, which like I've found to add up to like 150 milliseconds of latency, which is crazy. But yeah.
Yeah, tmux is bad. I used it a couple times before when I had to use it back in the day, and it was slow. You can notice the difference.
Exactly. Yeah, right. And so I think it's important to note that this is even before, like I actually have never seriously attempted to improve Psy's performance, and it's already like pretty good. So, it just goes to show that there's still room for improvement.
Yes, yes. So in your talk, you have talked All right, so Mike also have another question. What makes science most different, distinguished from ASCII, ASCII or script?
The biggest difference is that like Psi is a fully featured terminal multiplexer that that lets you access like the playback for your terminal session like live, like in your session. Like script and Ask Enema, like those are great for like recording a session and then through some functionality going back and like watching it later. But like this is the time travel is the core feature of Psi, right, as a terminal multiplexer. And so that's the advantage. And obviously like neither of those applications allow you to like search through all of your history at once and like jump back to like a particular point and that sort of thing. And so it's sort of, it builds on the precedence of those programs, but it's entirely different.
Great. So in your talk, you are talking about the first attempt, and you said that the regular expressions matching and it is low, and it's long. Can you explain it? I think that will really have all the students here in the audience, because we also work in my other projects. We also touch a little bit with the regular expression. So that would be beneficial for students.
So go back and I can cover that section in a little bit more detail again. Here, let me open this up in the slides. Let's see. Yeah. Let's see. Because this is actually a bit of an unusual use of regexes. At least I could basically find no information online about doing something like this.
Yeah.
Let's see, let me pause this up. Okay. Yeah. So this slide again, it's really hard to understand, but yeah. So the basics is that what I was describing was a way of using partial execution of a regex engine, right? So you compile a regex and then like it basically like is a state machine that like takes a sequence of bytes and then decides whether it matches the regex, right? And so what this is doing is like when say for example in this pattern right here, when it sees a B, it's like, well, that byte was accepted, right? And so it becomes like a partial match and like the regex machine is not halted, right? Regex state machine is not halted. And so what like we can just like leave it sitting there, right, in memory until like another character, like for example, like some other character is like written to an adjacent cell, and then we run the regex, like we basically like accept the next byte and say like, well, is this byte accepted by the regex state machine? And it doesn't halt, right? It doesn't just quit. Then it becomes a further portion of this like partial match, right? And then when we see the last one, it's like, okay, the regex machine is halted, and it says like there's regex state machine is halted, and it says that there's a complete match, right? We now know that like these three adjacent cells are a complete match. And so after it is a complete match, you don't have to do you don't have to run the regex state machine at all anymore, right? You just know that like these particular cells, so long as they are not affected by any mutation of state, just retain their status as like a full match. And so, like I said before this slide, I think translation does not affect a match, right? So if it gets moved up or down on the screen, such as by scrolling, then it'll be okay.
Excellent. Yes. So
I see there's like some questions here. Sorry.
Yeah.
Have you documentation read up? Yeah, I do. So I have approximately, I don't know, I think it's something like 15,000 words of documentation on the GitHub site. I'll actually post that on the GitHub page here, GitHub repo. And the documentation is linked there. I'll actually just link it here. Yeah. And so I put a lot of effort into making the documentation good because, that's pretty much the only hope that an open source project has. So the other questions, built-in safeguards for auto-deleting specific types of sessions. This is actually something I've thought about a lot, but have yet to like truly implement because like I'm uncertain as to like what folks would actually need. I think like the most basic example of this is like what it could do is just blank out IPs. So if it notices that like some, it matches like some regex, right? For example, like an IPv4 string, right? It would just blank that out and like it wouldn't actually store those cells, right? So to speak. And that's something I've thought about. I also think that like, so you actually can selectively disable recording in certain sessions in Psi. So like it will never write anything to disk. So that's another thing. That's just like a built-in feature, which I thought was important. So if you want to turn off recording, you can. It doesn't have filtering options to remove commands that had errors, and so this is actually like kind of a, it is a, how do I put this? It's a bit of a rabbit hole of a question, because Psi's command detection does not actually do anything fancy when it comes to like in understanding the shell that you're using. It basically uses like visual heuristics to decide where like command output begins and ends. And so as a result of that, it actually doesn't even know like the exit code of like the commands that you run. It doesn't know like whether a command succeeded, right? And that actually was kind of an intentional design decision because like I wanted to support as many shells as possible without actually having to install Psi on the target system, right? So for example, this like, when you SSH into a remote system, as long as that system has it outputs like Psi's special sequence whenever a prompt happens, right? You'll actually be able to like Psi will actually detect those commands correctly. This is like, we're getting into the weeds here because it's a very hard question to answer, but I'll actually just like pull up the documentation for exactly that question and you'll see what I mean by that.
Sure.
It's probably easier. Yeah, that's here. Anyway.
Okay. The comment history. Great. Is there any other questions from the audience? All right. So, Caleb, we missed our face-to-face audience here, missed Caleb's introduction. So Caleb has very, very interesting journey in his journeys from from the startup to
Sam.
So can you share with us a little bit of like the life in startup, because he worked for the startup that actually went IPO, went public, so that it will help our students here to choose different paths.
So talk about the startup path, startups.
Path.
I'll describe this like very basically. So I basically lived the Silicon Valley dream, right? Like I left school and I had this dream of moving to the Bay, and somehow I got an interview at this tiny startup, which I think it had like eight or nine employees at the time, and we were in a literal garage, and we had like one vehicle, a semi truck, right? So like the front of a semi truck that's called the tractor, right, in a garage. And that was kind of like where like the company got its footing. And so I think like we had we were consistently able to like raise capital from storied investors, and I think that was part of the key to our success for sure, because we never actually like ended up making any revenue, right? But anyway, so it was a really like exciting experience of just like working on deep tech and doing something really interesting and spending dozens of hours in the desert on a vehicle as it drove itself, and that was pretty cool. And yeah, so I also learned a lot. And I think the key about being at a startup, especially that early, is that like you really do have to learn quickly, and you're put under a lot of pressure to get things done. And I liked that, and I actually still managed to find like a semblance of work-life balance. So I wouldn't really say that's the issue. and it was just it was a great story. And so ultimately we went public. I had the privilege of standing on the NASDAQ stage with them as we, I guess, like when the market started in the morning or whatever. I actually don't even know what that event is called, but basically it's this big thing because we were listing right on the NASDAQ, and so that was cool. And yeah, it was a great experience. And so I don't think that like it'd be very hard to advocate moving to Silicon Valley from the position of like this is going to happen to you. It probably won't, statistically speaking, but I still think that it's just like a fantastic environment for where you're surrounded by people who are all doing interesting things. And I should like differentiate like the version of Silicon Valley comprised of startups from like that of like corporate, because like there's a lot of folks that move out and work at the big tech companies, and they just have like a very different experience. I think people are still excellent there, but I would say maybe somewhat controversially that your technical skills won't be as challenged as they would be at like a deep tech early stage startup. And so AI has like taken a lot of the air out of the room, I think, right now, and it might be an interesting time to go work there, but at least like there's a lot of capital flowing again, so that's something.
That's great. That's great. Yes, that's exactly what I would like my students to hear about, because not only you are like one of the founder. If you make it to the New York Stock Exchange and ring the bell, you are one of the
yeah, ring the bell. That's what it is. I can't believe we got that.
Yes.
Yeah, we ring the bell, and so it turns out that it's not a bell. This is very
Okay,
disappointing.
really?
It's not a bell. Like it's like it's kind of crazy. I don't know how they've done this, but like it's like a screen that you just touch, and so it's really
That's the real
anti-climactic.
bell.
It wasn't a real bell. I'm like, why do they call it ringing the bell? But I'll tell you, the bagels at the NASDAQ were great. So that's a memory that stuck with me. So
That's great. I feel very, very happy for you, and I can't wait to hear about the journey that you use with your John Hopkins Master and 6 languages.
We'll see if I end up using them. We'll see if I end up using. Yeah, I'm presenting.
Good night, Caleb. And on behalf of our faculty and students, big thank you and very, very grateful. Whenever you go back to Wisconsin to visit your family is still here, right?
That's right. Yeah.
Yes. Whenever you go back to Tucson, let us know.
Yeah, I'll come back to visit. Yeah, for sure.
Yes, let us know. Thank you, Caleb. Have a good night.
Thanks a lot.
Thank you so much. Yep. Bye-bye.
Bye.